welcome back to the lecture series in cell culture technology. So, today we are into the 8th week, which is essentially the final week of it. So, the way I have designed this week is we will have multiple small modules of 20 to 21 minutes, and there will be few extra modules apart from these 5 classes scheduled for the week, which I will be adding up to it, which will help you to understand the current or I should say the most advanced technologies currently followed all over the world, or at least emerging, which will definitely change the face of cell culture technology in the next 20 to 25 years. And I wish all of you should be braced up for that, because that's your generation when you really have to know how these technologies can come very handy. So, the first lecture today will be follow up on what we finished in the last class. So, if you remember in the last class we talked about growing different kind of muscle cells, skeletal muscle, we talked about the cardiac muscle, and we talked about how the sliding filament theory works and how the muscle contracts and everything. But what is important for us to understand, most of these excitable tissues includes the neurons, skeletal muscle, cardiac muscle, smooth muscle, some of the endocrine cells. Not only they have electrical activity, they indeed show mechanical activity, especially the cardiac myocytes, skeletal muscle, and I told you about the development of the skeletal muscle where they form small myotubes, then myotubes become myofibers, myofibers become what you see multiple myofibers joining together to become a muscle. So, if they show contractile activity, which is mechanical activity, anything which shows some form of mechanical activity generates a force. So, based on the force, one can essentially figure out what kind of muscle it is. In other words, just to take you a little bit to the molecular side of it, while we were discussing the muscle, I told you the muscles are made up of 2 key structural proteins, myosin and actin, or actin and myosin. So, during sliding filament motion, it is the actin and myosin chains are sliding over one another. Okay. That I told you that you can look through any textbook, you will be able to figure that out how that works. Or as a matter of fact, if you go to Google and say sliding filament theory, you will be able to figure that out. So, this sliding motion of actin and myosin over one another is a function of the muscle type. What does that mean? So, the speed with which the sliding is taking place on between the myosin and actin through the myosin heads is a function of the muscle type, or in other word, that speed determines at what rate it is going to contract. So, when we talk about the contraction, we talk about the speed of this movement, we are essentially talking about the force being generated by the muscle in that whole process. So, and that force, so let me formalize it, form of the text. So, we are into week 8 and lecture 1, W8L1. Okay. So, what we are trying to do today is measuring the force generated by muscle. It could be skeletal muscle, it could be cardiac muscle, skeletal, cardiac, smooth muscle, measuring the force generated by muscle in an in vitro cell culture system. This is the topic what we are going to discuss, and what all points I kind of highlighted. I told you that whether it is a skeletal muscle like this, skeletal muscle like this, or a cardiac myocyte like this, cardiac myocytes or cardiac tissue, myocytes or cardiac tissue like this, they are made up of actin and myosin filaments, and these actin and myosin filaments slide over one another. Okay. Actin, myosin, and these myosins have the myosin heads which are kind of connected like this, likewise. Okay. So, similarly here you have the actin and myosin. Okay. So, now these actin and myosin essentially leads to what we call as, there is a sliding motion between actin and myosin filaments. These sliding motion between actin and myosin filaments leads to what we talked about, contraction, and this contraction is nothing but this contraction has a force. Now, this force essentially determines, this force is different for cardiac tissue, this force is different for skeletal muscle. So, if this one I called it as FC, this is FSKM, okay, CM for cardiac muscle. Now, how our question is how you can determine these two forces in an in vitro cell culture setup. So, now having said this, why are we doing it? Whenever we try to do something, one has to first of all justify. So, say for example, one wants to screen drugs or screen phenotypes of myotubes for muscular dystrophy or any kind of muscle related disorders or other muscle disorders, one needed a tool. Just the way we have the cell culture tools which will tell you the cells are growing or not and how they are growing. You needed a very specific kind of tool to do so. A tool from where you can measure the force. How you can do this? So, say for example, you have this different kind of muscular dystrophy mice, different mice mutants. Muscle disorder, you have different mice mutants, mice, rat, whatever you want to use. Okay. Now, what you can do is you can use these to grow myotubes. So, I have already talked to you. Myotubes are the smallest unit of muscle in the case of skeletal muscle. These are the myotubes. Grow myotubes in a dish. Or you can suppose you want to screen drugs. So, you have this culture. So, you are putting different kind of drugs and measuring the contraction. So, what you are essentially doing is by measuring the force generated during contraction, one can evaluate the above effects. Now, globally, there are different kind of techniques which are being used, but today I am going to share one technology which I had the privilege of being an integral part of developing. That technology is called microfabrication of cantilevers, and using cantilevers for measuring the force generated by the muscle. So, this falls under microelectromechanical systems or MEMS based systems, which are very frequently nowadays used. You all must have heard about this word at some point or other, called biomems, okay, where M stands for micro, E stands for electro, M stands for mechano or mechanical, S stands for systems, micro electromechanical systems, bio. And when on these MEMS you have a biological component integrate to it, you have the possibility, or you have the technical know-how, or you have a scope to measure any kind of mechanical as well as electrical phenomena in a microsystem, because all your biological samples, if you are dealing with, if it is a cell, then we are talking about micron dimension, anything between 10 micron to, it could be less than 10 micron, of course, I mean say 2 micron to 10 micron to 100 to 500 micron. So, these are all microsystems. If you talk about much more smaller system, nano, then you have to go to NEMS, nano electromechanical systems. Okay. So, your structures which you are making are very small structures. Okay. So, depending on at what range you are developing these devices. So, these are devices on which you are integrating a biological component. So, in other words, the next generation cell culture where it is heading, and that is what we will be discussing in these last few lectures, is more on the area of technologies like what I will be talking mostly here: microfabrication, lithography, microchannel technology. We will talk about this regarding hippocampal neuron, microchannel technology, and advanced electrical systems, where we will be talking a little bit here and there about planar micro electrode array and little bit literature I will give you about field effect transistors or FETs in cell culture. So, let us start off with microfabrication. What is really microfabrication technology and how it comes very handy in microfabrication. So, earlier just few minutes back I told you we used micro cantilever systems. Okay. Essentially, what are cantilevers? Cantilevers are, all must have heard about AFM, right? So, cantilevers are something, some structures like this. You must have seen bridges. There are no pillars in between and it is kind of a hanging bridge, okay. And they say they work on cantilever principle. Those of you have heard about Howrah Bridge, the old Howrah Bridge. The bridge is something like not a single support system. So, these are those bridges which are based on cantilever principle. In other words, where all the force components are kind of fold like this. Okay. So, cantilever essentially, so this is just for your understanding sake I just gave it. Cantilever are essentially a very closest analogy what you can draw is, imagine in a swimming pool you must have seen these diving boards, right. There are diving boards like you stand there and it moves like this. Imagine a diving board of a swimming pool. So, if this is the swimming pool you have out here, this is the swimming pool underneath. So, this is where of course, one second. So, this is where you are standing. So, you must have seen a person kind of standing here and this moves like back and forth like this, and then this person jumps into the water. So, essentially this suspended plank on which this person moves, this is called a cantilever, which you can physically see. Now, think of it, I reduce the size of this cantilever to the level of micron, and once I reduce the level to a micron level, say I make it say 200 micron, or I make it 500 micron, or I make it 100 micron, depending on how far I want it to go. I can go up to 50, I can go to 20, depending on, again this all depends on what is your needs and requirements. When I develop these kind of micro cantilever, so then these are called a small mechanical devices or micro cantilever devices. Now, on such micro cantilever devices you can use such. So, the way you make it is, so now the question is how you really develop these kind of structures. So, there are multiple ways by which you can do it. One of the ways what we followed is, say for example, you take a block structure like this. We use silicon. So, I am just giving example of silicon, and then what you do, you have a mask which have a pattern like this. Okay. So, now you place the mask and using laser or other etching techniques is started to etch out the surface. You are continuously etching out the surface. As you keep on etching out the surface, the resultant stuff will be like this. You will have an array of micro cantilever which will be etched out from the surface, of course, with a certain amount of depth profile which will be out there. Okay. So, there is a depth component associated with it, and that could be seen here. This is the depth. So, that depth could vary from, say, I would say anything between, again, anything between these numbers, depending on how much you want to do it. It could be 1000 micron, that you can always vary. So, with this background, I will close in the class. In the next class, we will integrate some of the tissues into it, and we will see what all power the system can offer you. Thank you.